Ever wonder how your phone gets better at understanding your voice, or suggesting the perfect song without sending your private data to a server? That's federated learning in action, like a group project where devices team up to build a smarter AI, but keep their data to themselves. But here's the twist. When devices share updates over the internet, delays or dropped connections can throw everything off. How do researchers keep this process smooth? Let's crack the code. Federated learning works by letting devices like your phone or a smart sensor train an AI model locally and only share changes to the model, not the data itself. Think of it as collaborating on a report. Each person works on their section and shares just the highlights, not the whole draft. But here's the problem. Sending full updates is slow and uses too much data. Enter Quantized Federated Learning, a clever shortcut where devices compress their updates, like summarizing a report instead of faxing the whole thing. It's faster and lighter, but what if the summary gets lost in the mail? That's where this research shines. Imagine a team of students working on a project with spotty Wi-Fi. They share quick updates, but some messages fade or lag. How do they still end up with a top-notch final project? The answer lies in math. The paper shows that even with compressed updates and unreliable connections, the AI model can still converge, meaning it keeps getting smarter over time. It's like having a secret recipe that keeps the project on track, no matter the bumps in the road. So how did they make this work? The team tackled two big hurdles: delays, slow internet, and outages, no connection at all. They used equations to model how these issues mess with the AI's learning and built a system that adapts. It's like having a backup plan. If a device's update vanishes, the system fills the gap with previous data, so nothing gets lost. The real magic. They didn't just test their idea, they proved it mathematically. Let's get technical. The researchers developed a mathematical framework to analyze how model pruning, gradient quantization, and wireless power control interact. Model pruning is like trimming a neural network's branches to remove redundant computations, making it lighter and faster. Gradient quantization compresses updates by reducing precision. Think of it as converting a 4K video into a low-res thumbnail. Wireless power control optimizes energy use during transmission, ensuring devices don't drain batteries. Together, these techniques create a feedback loop that balances speed, accuracy, and energy efficiency. Their experiments showed LTFL outperforms existing methods, slashing delays by 40% while maintaining 95% accuracy. This means smarter AI on your devices, whether it's your phone recognizing your voice or a smart thermostat learning your schedule. And because it's designed for real-world networks, it's more reliable than other approaches. No more dropped connections or endless loading screens. Now, while this study was done in controlled settings, the team wants to test LTFL in real-world wireless networks, like your phone connecting to a smart home. They're also looking into adapting it for massive AI models, which are the future of tech but hard to train from scratch. Think of it as a way to fine-tune a giant AI with the same energy as your phone's battery. As AI becomes more embedded in our lives, think smart cities, medical devices, or even space exploration, efficiency is key. LTFL shows us a path to smarter, faster, and more sustainable AI that respects privacy and saves resources. Next time you use a feature that learns from your habits, remember, behind the scenes, innovations like LTFL are working hard to make that possible, without asking for your data. Thanks for watching and stay curious.